Right, good morning, everyone. Welcome to the last lecture for ED 2001. Right, so last week we started on ADC, right? So now we are, I think, halfway through. So last week we talked about the number of quantization levels, then the resolution, and the quantization error, right? So we are going to work on an example, right, on this. So if there's any questions, right, just let me know along the way, right? So let's start with the example here, right? So we have analog to digital converter, right? So using 4 bits for quantization. That means you are going to have 6 0 0 0 0 to 1 1 1 1, right? To represent the analog signals. Right, so what do we have here, right, is the question is asking for the number of quantization levels, and that is should be quite straightforward, right? So from 0 0 0 to 1 1 1 1, right? So we have, okay, so the quantization levels, that means how many levels can I split the analog signal, right, that comes in, right? So let's say given that the signal goes from 0 to 5 volts, then how many levels can I divide that analog signal into? Okay, so that will be 2 to the power of 4, which is 16 levels. Okay, now so that's for the first part, which is quite easy. Now, what about the resolution? Huh? Right, let's say resolution. Now, resolution is what is the gap between each level, right? So now the question doesn't give you the voltage range, so I need to give you the voltage range. So example, if the voltage range that is coming in that you expect is from 0 to 5 volts. So the analog voltage range that is coming is from 0 to 5, right? So the resolution will be 5 divided by 2 to the power of 4, right? That means each of the level that we have here, right? This is what we call the resolution, right? From 0 0 0 0 to 0 0 0 1 to 0 0 1 0, and so on and so forth. Okay, now so that is going to be 0.3125 volts. Now, so that means it's a very simple question here. So if I want to have a more precise signal or something that is a better resolution, right? Then I will need more bits to represent that. Okay, then you need more quantization level, okay, and more bits. Okay, right. So what is a quantization error here? Now, because when you are doing analog to digital conversion, don't forget there is some error. You're rounding. In our case, in the examples that we showed, in the circuits that I have used, right, all rounding down. Okay. Now, so what happens here is for the quantization error, right? There is rounding. Okay, so there is an error when you go from analog to digital, right? You can't be exact because unless you have infinite number of levels, right? If not, you will not be able to represent an analog signal completely, right? Or exactly, right? So what you are doing is there will be some estimation, and that error, we call it quantization error. It is plus minus the resolution divided by 2, right? Don't forget we are rounding off. So when we round off, right? Example, when you round off a number, right? 1.5, you round to the nearest integer, it will be 2, right? 1.7 round to the nearest integer 2, right? 1.3 round to the nearest integer 1. Okay, so the quantization error down here is plus minus 0.3125. Now our case, right? The circuits that we are using are all rounding down. Rightfully, the error, right, should be the entire resolution from 0 to the in this case 0.3125. Right, but whatever quantization error that we work with, right, is going to be a general quantization error that pertains to all types of ADC conversion, based on rounding to the nearest integer or rather than rounding down. Okay, so that is why the quantization error is plus minus 0.3125 divided by 2. Okay, I hope everybody gets that. Okay, so moving on. Right, so from here, then you can calculate the value. Okay, so that will be the quantization error. Okay, why divide by 2? It can take note that the circuits that we are using is rounding down. Okay, but in general, example, let's say, okay, let's say I'm going to go for this is the voltage. Okay, so example, I have a signal, something like this, and I am going to sample at different points. So maybe I'm sampling down here. I'm sampling down here. I'm sampling down here. Okay, so when I'm sampling down here, I will round down. Okay, now in this case, I'm talking about a case whereby you have the rounding off. But take note that the circuits that we are doing is truncating. I'm going to show you in a while the difference. So rounding off means what? Like if the voltage that I sample here is lower than 0.5, right? Then the digital level that you will be quantized to will be 0, 0, 0. You're rounding down. Okay. Now, but in the second case, if the voltage sample is more than 1.5, then you are rounding up. Okay, understand what's going on? Now, so what happens here, right? You can say that the possible error of quantization will be plus minus 1 volt divided by 2. Agree? Because you're rounding up or rounding down. Understand? Whatever resolution that we have, this is the resolution, yes? Because you're rounding up or rounding down, right? So the difference is 0.5. The maximum error will be 0.5. Can? I hope you got that part, right? Now, but whatever circuit that we are using here, right? We are rounding down, if you still remember, right, from last week. Whatever you have, let's say this is your signal, and I'm sampling here, sampling here, sampling here, right? Based on last week, right? Whatever that we talk about, right, is everything is whatever that is sample here will be rounded down, or we call it truncate. Okay, so then what is the error? The error will be 0. The maximum quantization error will be 0.3125. Yes. So listen. So what's happening here, right, is that quantization error, right, is based on what? Is based on theory. Because your ADC is based on the point that ADC is rounding off. So this quantization error, the calculation method, the quantization error is based on what? It's based on rounding off. So rounding off, you can round up or you can round down. Example, if I have 0.5, I round up to 1. If I have 1.2, I round down to 1. This is round up, this is round down, right? If I have 1.7, I round up to 2. Okay, if I have 1.3, I round down to 1. Okay, so what we are saying here is the quantization error, okay, will be plus minus of the resolution divided by 2. In theory, can Now, but a lot of the ADC, right, we do truncation, right? Example, 1.2 truncate to 1. Okay, let's say the resolution is 1 volt. Can I say again, if the resolution is 1 volt, then 1.3 truncate to 1. 2.7 truncate to 2. So this is a truncation. Everything goes down. Okay, so in that case, the error will be 0.315, right? So that is what we call the truncation error. Now, but this quantization error that we are calculating, is based on a theoretical value. Okay, so we stick to this convention when we calculate quantization error. So we do not calculate based on the quantization error, the truncation error. I hope everybody gets it. Okay, now so take note. So when we talk about quantization error, it is always a theoretical value whereby it is rounding off and not truncation. Okay, now so okay, if you are good on this, let's move on already. Now, so what kind of ADC circuits that we can have, right? So the first one that we're going to talk about is what we call the flash ADC or the simultaneous ADC. So what's happening here is we're using comparators. Now you guys, we went through op amps, right? So we have op amps lined up here. Now we're going to talk about that in a short while. What these op amps are doing, right? What these op amps are doing, right? So we have high-speed comparators, right? Now, it is comparing a reference voltage, okay, with the input signal. Now, where is the input voltage here? Now, if you look closely, I guess, from the circuit here, this is where the input is. Okay, let me write down. So this is your V input, right? So this is your input voltage. Right, it's connected to the positive terminal of the op-amp comparators. Now, then what do you have next, right? This is the reference voltage. Now, if you look at this is like a voltage divider. Okay, so this is like a voltage divider. So you have 1, 2, 3, 4, 5, 6, 7, 8. So basically, you'll be dividing this voltage, right, by 8, right? So let's say this is 8 volts. Then this will be 7, 6 volt, 5, 4, 3, 2, and 1 volt. Can? Now, so what you are doing here, right, is that you are comparing your input with 7 volt, comparing with 6 volt, comparing with 5 volts, comparing with 4 volts, comparing with 3 volts, and 2 volts, and 1 volt, and so on, so forth. Now, so what will happen here is this. Now, what you are doing here is the V of each comparator, right, is equals to the V plus subtract the V minus. Can? And amplify by the open loop gain of the op amp. Can? Now, so what's happening here is this. If the voltage input is higher than the voltage at the negative terminal, the output will be a 1, okay, or a high voltage, okay? Now, then if it's lower, then what happens is that then it will be 0. Now, so what will happen here is example, if the voltage input is 2.7 volt, right? So you guys tell me, which of the op amp will give an output of 1 or high? Okay, which one? Counting from the lowest one, right? Let's call this op amp 1, 1, 2, 3, 4, 5, 6, 7. Okay. Now, so say this is 2.7 volts. So which of the op amps will give a high output? Right? Anyone? Okay. Is it the reverse? Now, see, the input is 2.7 volts, right? So V out is equals to the gain V plus minus V minus. Okay, so the answer should be which one? This one will give you okay, let's say we use logic. So this will be 0, 0, 0, 0, 0, 1, 1. Okay, don't forget this is 2.7 volts. Okay, so we are saying here, if this is 2.7 volts, this is higher than the 1 volt, output will be high. Okay, and this is 2.7 volts, negative terminal is 2 volts, output high. 2.7 volts, this is 3 volts, output will be a low because the 2.7 is lower than the reference at this point. Can? So now, so what will happen here is you will get 0, 0, 0, 0, 0, 1, 1, which will go into an encoder, right? Then give you the output here, right? So 0, 0, 0, 0, 0, 1, 1. Now, what will this encoder do is it will look for the highest comparator that will give you a 1. Okay, so the highest comparator here is the second one. Okay, now, so you can see here, right, at this node here, right, is your 0, the 0 level. So this is 0, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, and 1, 1, 1. Okay, so what will happen here is corresponding to this, your output here will be 0, 1, 0. Understand? That means it corresponds to the digital level 0, 1, 0. Understand that? Can? Now, so what happens here is when the input voltage exceeds the reference voltage, right, a high is generated. So what will happen is the encoder will look for the op-amp, the highest op-amp that will give you a 1 or a high. Then you will encode that particular comparator accordingly. So in this case, right, it will be 0, 1, 0. The output of the encoder here will be 0, 1, 0. Okay, now let's just do one more. Let's just do one more so that you guys are clear on this. So let's remove all this here. Okay, let's remove all this. Now remember, we are trying to digitize, okay, our signal here. So let's say, okay, this time round my input voltage, right, is 5.3 volts. Okay, so now can you tell me which are the op-amp comparators that will output a high? 1 to 5, that's correct. So these will be high. Now, because this is 5.3 volt, 5.3 volt, right? So you will realize that these two will be 0. Now, so what will happen is it will take the highest op-amp here and encode its state. So this one is corresponding, this is 0, 0, 0 again, right? 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, and 1, 0, 1. Okay, so the output here will give you a digital level of 1, 0, 1. Okay, so understand. So what we have here, right, is a row of op-amp comparators, then goes to a encoder, and from the encoder, it gives you, okay, the binary output for that particular voltage level. Right, so what happens here is if I want a 3-bit, right, let's say the digital levels are represented using 3-bit, or the quantization level is 3 bits, right, then we will be using 7 comparator circuits. Now, you do not need one for the 0, 0, 0 condition, because you don't have to. You don't have to. Okay. So right, so let's say if the signal is comes in is, let's say, in this case, let's say it's 0.1 volt, right? Then it will automatically be 0, 0, 0 in the output. Right? So now in this case, right, if I want a 4-bit converter, I will need 15 comparators. Right, to the power of 4 subtract 1. Okay, now so this is the flash ADC, right? Now, so a little bit more information about the flash ADC, right? So the reference voltage is actually this part here is what we call a voltage divider circuit. Okay, it's dividing the reference voltage into 8, right? So if it's 8 volts, then each of these will be 7, 7, 6, 5, 4, 3, 2, 1. If it's 16, then it will be double, right? 14, 12, 10, 8, and so on and so forth. Right? So it depends on how many levels you want to quantize, right? So whatever VREF comes in here, right? So the voltage here will be just divided by 8 accordingly. Okay, so the output of each comparator, right, is connected to the input of what we call a priority encoder. So what will it do is it will look at the highest op-amp. It will look for the highest op-amp that has a high output, and it will code that state into a binary level. Okay. Now, take note that this encoder is not always active. It's only active when there is an enable pulse. Okay, when the enable pulse is a high, right, then the encoder will do its work. So it will not be encoding continuously. It will encode only during the enable pulse. Right? So right, like I mentioned, the encoder will output a 3-bit code, right, depending on the value of the highest op-amp that gives you a high. Okay, so the binary code is based on the highest order input, which could have a high level. Okay, now, so let's do one example. I think a little bit of more information here. Okay, I think I can skip this page. This is just talking about the ADC in general, right? So the frequency, right? The frequency will determine how accurate this ADC is, right? Okay, let's go to the example straight away. Now, let's take a look at the example over here. Okay, and I'm going to do the very first part, then after that, I will need you guys to try on your own. Right. Now, so take a look at the first one, based on the analog input voltage. Let's see. So these are where the enable pulses is. So the priority encoder is only active during each of these positive pulses. Okay, so let's take a look at the first enable pulse, right? Now, the voltage is here, right? So now I want to ask, right? What will be the analog input voltage that it will be to? Based on, very good, it's 4 volts. That's correct. Okay, so remember, these are all the different voltage level that you will be quantized to eventually. Okay, so I don't care what voltage that you have here. Let's say this is 4.28, right? But digital, for this particular case, there is no 4.28. There is only 0, 1, 2, 3, 4, 5, 6, 7, 8 volts in the digital world for this particular ADC. So it will have to approximate it. And in the ADC that we are doing a rounding down. Okay, so the digital level that you will be rounded to will be here, 4. Right. Now, then if it is rounded to a digital level of 4, okay, what will be the binary output? Right, a 3-bit binary output. Yeah, 100. That's correct. That's all. Right. So what do I have here, right, is that at the first pulse, my output, right, is going to be 1, 0, 0. Okay, so down here, 1, 0, 0. Okay, now let's go to the next one. Next one, what level will it go to? 6. Very good. So you're going to 6. Okay, and the binary output that correspond to this will be 1, 1, 0. That's all. Okay, so this is quite straightforward. So this one stays as 1, then goes to 0. Now, then you can do this for the rest of the questions. Okay, so let's take a look. Let's see. The next one will be 7, right? And that will be 1, 1, 1. Okay, so 1, 1, and 1. Okay, so right, so we can continue doing. I'm going to write down the levels here. Then after that, you can slowly sketch. Right now, so let's take a look at this particular one that okay, so this particular one here. Now it is lower than 1, above 0. So this one, the quantization level will be at 0, 0, 0. Right? So in this case, all your op amps, right, the output will be zeros. Okay, so that's why you get 0, 0, 0 down here. Right. So the rest will be easy to finish up on your own. So you can do that on your own. Okay. The next one, this is a little bit more, has a little bit more intelligence built in. The other one is pretty much brute force, right? So you have one entire row of comparator, then just compare, then after that use an encoder to come out with the output. So the next one that comes, right, is a very, very smart usage for the of a ADC. It's a very smart design, right? This is very widely used. So this is what we call the successive approximation ADC, right? So we just call this SAADC. Now, so what happens here, right, is that this ADC, right, consists of a DAC, which is a digital to analog converter. Now, I know that I've not talked about any of these digital analog converter yet. So basically what we have been talking about is just from an analog input convert to a digital output. That's all. So it should is ADC. Now, so for DAC, right, is the reverse, right? From a digital signal that you have digitized, you want to send it out to maybe a speaker, right? Or you want to send out as a voice signal, then you need to recover the analog back, right? So that is what we call a DAC. Okay, so you are for DAC, okay, maybe I should give you a example. So ADC, right? Maybe 5.3 volt. This is random. Now come out, what is the output? The output is binary bits. This is just random numbers. Okay, so this is the analog world. You get a voltage. You want to convert to a digital output. So this is what we call a ADC. Now, then what does a DAC do? It takes whatever digital input that you have, right? Let's say you go through a DAC, you recover back the approximated voltage. Take note, it's the approximated voltage, it's not the actual voltage. So go back into the analog world. Maybe you approximate to 5.25. Okay, so this is what we call the digital to analog converter. So when I'm doing the input is 5.3 volts, but let's say my quantization level is not at 5.7, it's maybe at 5.25. So after going through this, then come back, the DAC will give you 5.25. Can I hope everybody gets that. So remember, the ADC process is always approximate, right? Because there's truncation in the process. Okay, so now, so what will happen here is this. Should I go through this page or should I just... Okay, let me see. Okay, I think I should just straight away go to the example on the next page, because this operation, right, describe what is happening on the next page. So if anything on the way, you please just stop me and ask, because this is a process. There's a procedure involved here. So any step you're blur or cannot catch, just stop me. Okay, so what do we have, right, for this ADC? Remember, we are converting analogs to digital. So now, so what is the input here? Okay, so what do we have here? The input is 5.1 volt in this case, which I'm connecting to the positive input of 1 op amp. Okay, now if you compare to the previous flash ADC, you have so many. So if I want 4 bit, right, I will need 15 op amps. If I want 5 bits, I will need 31 op amps. If I want 6 bit, I will need 61 op amp, 63 op amps. So there's a lot of op amps to deal with. Okay, now now you try to go like 8 bit. 8 bit is quite common, even up to 16 bit, right? You have to ask yourself how many op amps you need for that case, right? So it's no longer practical, right? When you have like 16 bit or 32 bits or even 64 bit, right? It is not practical anymore, right? So what we are going to do is this is the circuit, right? So the input 5.1 volt is input to an op amp, and it is comparing with a signal that comes from the DAC. Now, so what happens at the very beginning? Right? What happens at the beginning, right, is that you will set. Now you see that there are 4 bits to the DAC. There's 4 bits to the DAC. So what's going to happen is it will start off with setting the MSB to a 1 first. Right now, say that the DAC has V out equals to 8 volt. Okay, 2 to the power 3, let's say 8 volt. Okay, but we have to understand that this 2 to the power 3 doesn't always need to mean 8 volt. It's just that this level 1000 for this particular example correspond to 8 volts. Okay, so let me write down first. So corresponding to 1000, we are saying that this is 8 volts. So 0100 will be how many volts? Anyone? So 100, yes, very good, 4 volts. Then 0010 is 2 volts, and so on and so forth, right? But what I mean here is only for this particular example, I can set to other voltages, right? So I can have a different reference voltage. So I can have, let's say if the voltage is much lower, maybe this one can be 1.6, this one can be 0.8, this one can be 0.4, and this one can be 0.2. It depends on the application. So in this case, we are saying that 1000 in the digital level correspond to 8 volts output for the DAC. Yeah? Can? So let's take a look at the first one. Right. Now, so from the DAC, the first thing that was set was 1000 and the output was 8 volt. Okay, let's fill that in first. Now, 8 volts is greater than 5.1 volt, right? So what will happen is the comparator output, the op-amp comparator output will be a low. Now, if it's a low, right, then what will happen, right? Then this MSB of the register here, this is a successive approximation register. Now, just take it as that this is just a register that holds numbers here, which is going to program your DAC. Okay, so now, because your input voltage is lower than 8 volts, right? So that means your MSB must be set back to 0. Understand? Because the input voltage is lower than this voltage here. Can? So we are saying that the MSB then will be set to 0. Okay, so now let's go to the second case. Set to 0 already. Then what happens? Then we are going to try by setting the second MSB to a 1. Right? Second MSB set to a 1 is a 4 volt. Okay. Now 5.1 volt, right? The DAC output will be 4 volt now. 4 volt is less than 5.1 volt. Okay, and then the output of the op-amp will be high. Okay, now since the input voltage is higher than that voltage, that means that I want that bit. So 2 to the power of 2 bit will be retained. The 1 will be retained. Understand? So this is like taking the MSB compare first. After that, then you take the second MSB go and compare. Compare already. Oh, if it's bigger than it, okay, then you leave it as 1. Can? So next, now you try the next level, right? You set it to 1. So, but this one you retain as 1. So you can see that this one is capped, right? And it's propagated to the next evaluation. So this evaluation here, right? You need for a 4-bit, you need to evaluate 4 times. Then the final code that you get, right? The final code that you get will be the one that will be the level that this analog voltage will be digitized to. So now we are going to set this to a 1. So 0, 1, 1, 0, the third MSB, we set to a 1. So anyone can tell me what will be the DAC output? No, not yet. Don't think about the reset first. Okay, so remember that now we are putting 0, 1, 1, 0 to do a comparison first. Okay, later then I talk about the reset. Okay, so now I put 0, 1, 1, 0. The output will be 6 volts. Why? Because it's 4 plus 2, right? 4 plus 2. Yes, that's correct. So the output here is 6 volts, which comes from 4 plus 2. Now, 6 volts is greater than 5.1. Then the output of the op-amp will be a low. So that bit will be reset to 0. So once you understand this process, right, you can do for any number of bits. And what you need is just a DAC that has a corresponding number of bits. You do not need so many op-amps in that case. Okay. So if you have let's say let me see. Yeah, let's say it's a 5-bit situation. You do not need 31 op-amps. You only need one op-amp, and you just need a DAC that can do for 8-bit. Can? Now, so next, we are going to go to the last level, which is 0101. That means the last, the LSB will now be set to 1 to compare, right? So this time round, it is going to be the 2 to the power of 2 and 2 to the power of 0. Add together is going to be how many volts? It's going to be how many volts? Anyone? Yes, it's just going to be 5 volts. And that 5 volts come from 4 plus 1, right? And 5 volts is less than the input voltage, which is 5.1. So the output of that will be high. So this is going to be retained, right? So what will be the final code that will be supplied to your DAC will be 0101. Okay, so 0101 will be the level that 5.4. Now, so I'm going to do a simple block diagram here. The input voltage in analog 5.1. So go through this ADC, it will be digitized to 0101. That's all. Okay, so this is quite easy, yeah. Okay, any questions on this before I move on to the examples? Okay. Okay, so now there is a flow chart on the next page, which I think there's no point, right? If you understand the concept, right? I think this is we can skip this, right? So let's go to an example on the next page. Okay, so guys, can y'all take a look at this question? Okay, now, so don't forget, this is still on our successive approximation ADC. Now, this is a 8-bit successive approximation ADC, right? And the resolution is 25 millivolt. So we're going to think about what that means. Now, so what we are saying here is you have, let's draw that circuit up first. You have, right? So you have a DAC here, then you have 3, 4, 5, 6, 7, 8. Then you have your register here. Okay, you have a register here. And okay, so what you are going to do is you're going to start with 1, 0, 0, 0, 0, 0, 0, 0, and you're going to compare. Right now, so the input voltage is 3.12 volts. So this is 3.12. Now, the resolution is 25 millivolt, right? So what we are going to say here is that, let's see, they're asking for if input of 3.12 volts is applied, what is the digital output? Now, I'm going to break it into two parts. This is part A and part B. Can? Now, so first question here, right? 0.025 volts. So what is the digital level that I need to define this particular voltage? Anyone? Resolution of 25 millivolt means what? Okay, guys, anyone? Now, think about it. Increase in 25 millivolt means what? So if 0, 0, 0, 0, right, represents 0 volts, so it means 0.025 volts or 25 millivolts. Understand that? Okay, correct. So the next one will be 0.05 volts. Okay, so now your input is 3.12 volts, right? 3.12 volts. Can I find which binary level it will be quantized to? It will be digitized to. Come on, guys, you can do it. Yes, 3.12 divided by. Okay, I think one of your classmates is sending me a direct message. So what you need to do is you just take 3.12, which is the input voltage, divide by 0.025, right? You should get 124.8. Right, now the question comes, 12. Now you want to convert, right? You want to convert from analog to digital. There will be something. Will it be 124.8? Right, guys, think. What will happen? Go. Will there be any rounding or truncation that happens here for this particular ADC? It will be truncated to what number? Yes, 124, that's correct. Not 125, 124, because it will be truncated, it will be rounded down, right? So what we have here, right, is the digital level that will be 124. Okay, and 124 in binary. So what is the digital output? It will be 124 in binary. This is the digital output. And let me see. I think you should get 0, 1, 1, 1, then 1, 1, 0, 0. Yes, it's always down approximation because you are comparing. You are doing a comparison, and the comparison, right, is the moment is bigger than the output becomes a 0. So it has to be lower. It's always a rounding down, or what we call a truncation. So see, maybe I do a little bit of explanation. For all the ADC that we have done so far, right? Example 124.8, truncate. 124.2, truncate. 125.9, truncate. Can? Okay, can, no problem. Now, so what do I have here, right? Now, every step, right? Every digital step that we are doing here, because it's 8-bit, so zeros, all zeros, then after that, I go to the next level, next digital level. the resolution is 25 millivolts, that means the next level, right? The next analog voltage will be 0.025. So 0.0000001 will represent the voltage level 0.025. Can 3.12 divided by 0.025, right? Which level will you be at? Come. Maybe I draw it out. So 3.12 volt, right, will be where? Now, so based on the digital level, yes, go to 1, 2, 3, 1, 2, 4, 1, 2, 5. Now, so the voltage, right, will be where? The voltage will be somewhere here. The analog voltage. Let's say the analog voltage at that point, right? Maybe somewhere here, right? This is your 3.12 volt. I'm converting to digital, remember? Right? So 3.12 volt, right? But based on the ADC circuit that we all have is all truncate, which is round down, right? So which level will represent that 3.12 volt? It will be the binary level 1, 2, 4. Understand that? Because it's rounding down, okay? Because this is, you're going through op-amp. The moment the input voltage is higher, then the output is high. The input voltage lower than the DAC output, right? Then your output will be low. So that's why it's truncate, it will be rounding down. Okay, quantization error, remember, the quantization error that we are calculating, right, is always based on rounding and not truncating. But what we are doing here is truncating. This is the textbook calculation method. And everybody has been following that since, because what we are saying here is now you can design an ADC circuit that round down. Then you can also design a ADC circuit that can round off and not truncate. What we are doing is truncating. Don't forget, we are doing truncating. So that is based on the theory that it is possible that maybe some people can design a circuit that can do rounding instead of truncating. So that theory is based on that, and the quantization error is based on that as well. Okay? No. Quantization error always calculate based on the plus minus resolution divided by 2, which is based on rounding off and not truncating. So we don't calculate quantization error based on the circuit that we are talking about. We will just use the plus minus resolution divided by 2. Understand? That is the theoretical way of calculating. Okay, I hope I explained this clearly. So take note, the quantization error is based on rounding off. So when you round off, you can round up, you can round down. That is why it's plus minus resolution divided by 2. But when you truncate, the error is the entire level. Understand? Yes, you're right. Okay, so the quantization error in this case will be plus minus 25 millivolt divided by 2. Of course, you will say, hey, actually, in this case, it is the truncation error is actually 25 millivolt, which I agree with you. Okay? Can? Okay, so whatever that you are doing when you are calculating quantization error is always based on a rounding off model and not a truncation model. Okay, let's move on. Now, so we already come to the point, but take note, this digital output, which is 1, 2, 4, it doesn't represent the actual voltage, 3.12. So now the question is asking, so what is the actual voltage from the DAC? So because 3.1 volt, well done. Okay, well done, good job. So the voltage from the DAC will be 124 times 0.025, okay, which is 3.1 volt. You guys are right. Okay, now so there are some losses here, okay, or there will be some approximation here. Now some people say that because of that, when you listen to digital music and analog music, right, it sounds different. So if you play something like from the very traditional way of sound reproduction, compared to now, because everything that we are listening to now, right, is digital. So they say there's a difference. Okay. Some of my friends who are those audiophiles, they say that they can hear the difference. I can't really hear much difference, but you do feel that the music that comes from analog reproduction is a little bit warmer. It's true, but I can only feel a little bit, but I can't precisely. Yeah, I know. But
it's just that small minor difference that makes a lot of things, because the headphones and speakers they use also will dictate what they hear out.
Yes,
Because what they
but
hear might be more flat compared to you hear the digital reproduction from a subscription service, all those,
I understand.
because of compression and whatnot.
But now if you go to like 64-bit digital, right? Can I can our ears still hear a difference?
Depends, because then
Uh,
again, do know that human hearing also do degrade over time and the
yeah.
spectrum on what you can hear is different.
Jordan is
So
saying that
maybe
I'm
what you
old.
hear is different. Then what the headphones they use is also boosting whatever they need.
Yeah, that's true. That's
Because they do run through an amplifier and the drivers they use is different. Spotify lossless also depends, because no matter what, end of the day, digital is still digital.
correct,
And
correct.
lossless, you must see what format you're using, FLAC or wave. Wave, no matter what, is still better than
Wow,
lossless.
you guys are like experts, huh? Maybe one fine day I'll need to go and ask you all which headphone I should be getting.
Depends, that one depends on personal taste, prof.
Also, one thing, right? Also, one thing is that a lot of the digital reproduction, right? They throw in a lot of smoothing features, so they smooth out the signal, right? So there is some ways that they are trying to recover. Yeah, but anyway, what we have is maybe there was one student who actually showed me the difference lah, and I could hear a little bit of difference. Maybe my hearing is already degrading, but I do feel that analog music in general feels a little bit warmer. It's a feeling. I can't really like pinpoint what is it, but it feels a bit warmer.
I
I
mean, prof, the easiest way to show is actually you
uh-huh.
listen to orchestra music at the actual concert and whatever you come out from Spotify and whatnot, there's of course a big difference. First, environment play a part.
No, but
Second, whatever they record is different.
that depends on your recording device, right?
No, it doesn't. Because no, I do in this field before. So
Uh-uh.
whatever you record, right, you
Uh-uh.
hear is actually the instrument raw output, but your external, whatever your audience hear may be different due to, first of all, speaker tuning. Second, also you must see what is the condition like. If it's warm or wet, or if not, is
Uh-uh.
the acoustics of the area is different.
Okay. True.
Because whatever they record through is they use a mic direct sent to into the recorder, so it
Uh-uh.
doesn't matter. So
And
whatever they
also
hear
don't
from the
forget,
mic is on.
don't forget that when you are live, when you're in a theater, right? You're hearing three-dimensional. You're not hearing a single or dual dimension kind of sound.
That's why the speaker do play a part and the tuning also comes with it.
Okay, I will learn from you guys on this. Okay. Hey, thanks for all your inputs. Now, we are going to do one more question for this, right? Then after that, no, I think it's two more questions. Then we are going to go to DAC already, right? Okay. Well, a lot of experts down here. I have also some students from the previous class. Wow, they are damn good at this. So they tell me which earphone to get if you want this kind of effect. What earphone you want you should get for another kind of effect, that kind of thing. Okay, come. Let's go to the next question. Now I have a uh 2-bit successive approximation ADC, same kind of circuit, but now only 2 bits. Now what do they want here, right? Is they are saying that the maximum ladder output voltage is plus 8 volts. Oh, sorry, can you change, guys? Can you all change the input? Change the input to 6.6 volts. Right? Then the question is asking, find out the binary states for the SAR, the sequence of the binary states for the SAR, right? Okay. So what do we have for the SAR here, right? This is a DAC here, goes to negative input. Now then the input is 6.6 volt. Then this goes to a register, which holds numbers or sequences to program your DAC, right? So, sorry, this is 2-bit, so I only need this. Okay, so let's go to the, okay, first, they want you to come up with the binary sequence states for the SAR, right? So what will it come up with first at the very beginning, right? What will be the output to the DAC at first? 1 0, that's correct. So it will be 1 0 to the DAC. Now, if it's 1 0 to the DAC, what will be the voltage that comes out from here? How much? Not 2. Now, can you see the maximum ladder voltage is 8 volts. So if it's 1 0, right, how much would it be? It will be half of 8 volts. Understand that? It will be half of 8 volts. Understand what I'm saying here? No, because when we say the maximum voltage, right, it's the maximum, right? The maximum. So when you have 1 0, it is one level lower. Okay, let me see. How do I explain this? Okay, so this is like that. So maximum voltage, right? Okay, let's so this will be 0 volt, 2 volt, 4 volt, 6 volt, and 8 volt. Understand that? Don't forget. This is okay. Let's go back to that page whereby you can see the ladder. Can you all see this? Right. So let me write down example. This one 8 volt. Then remember here is 7 volt, 6 volt, 5 volt, 4 volt, 3 volt, 2 volt, and 1 volt. So correspondingly, this is 0, 0, 0. This is 0, 0, 1. Then this is 1, 1, 1. Now can you see 8 volts is over here? The last volt that you are comparing with will be 7 volts. There's no point comparing with 8 volts, understand? Because whatever voltage that comes in, right, you are truncating. Don't forget that. You're rounding down. Okay, are we good on this? Okay, we continue first. Along the way, let's hope everybody gets what I'm trying to drive at. So what we have, right, is the 8 volt is what we call the reference voltage, which is the highest output, highest voltage. But when you do your ADC, it doesn't go to that level. It is only when you do a reproduction, when you smooth out the curve, then you can get the maximum voltage. Can? Okay, so whatever, when they say that the maximum ladder voltage is 8 volt, right? That 8 volts doesn't correspond to one of the levels. Okay, so we take this 8 volt, right? So this is how you do. You take the 8 volts, you divide by the number of levels. So now the number of levels is 4, right? 0, 0, 0, 1, 1, 0, and 1, 1. You take that voltage divided by that 4 levels, then you get 2 volts for each ladder. Can? Because there's only there's 8 volts, there's 4 states, so 8 divided by 4, 0, 2, 4, 6, 8. Okay, so 0, 2, 4, 6. Then between 6 to 8, right? Okay, you don't have a 8 volts because you will not compare with the 8. Are we good on this? Because you have to understand that we are rounding down. We are truncating. Okay, Okay, let's do the question first. Then along the way, if you have more questions, then feel free to ask. Okay, we are a little bit late already. So now what will be the inputs? It will go from 1 0, right? Then after that, the output here will be 4 volts. Now, do I keep this? I keep. Okay, so this one keep. Because the 4 volts is less than the 6.6 volts, and the output here will be high. So you keep. Okay, now you are going to go to the LSB. You're going to change it to 1. Okay, and if it's 1, 1, the voltage here will be 6 volt. It is still a high because your input is still higher than 6 volts. So you keep as well. So your sequence will be 1, 0 followed by 1, 1. That's all. Right, so these are the sequence of binary states in the SAR. Okay, now change the question. We are saying that we are going to start off. We are now going to have a 4-bit successive ADR, right? So what do we have here, right? It's going to be DAC again, but this is going to be 4-bit. 6.6 volts here. This is your DAC. This is your register, right? So we are going to start off with 1, 0, 0, 0. Okay, so in this case, if it's 4-bit, right? If it's 4-bit, then what will be the number of right? What will be the voltages? What will be the resolution? Anyone? 0.5, 0.5. 16 levels, 0.5. That's correct. Okay, so in the second case, it will be the resolution will be 0.5 because it will be 8 volts divided by 2 to the power of 4. So that will be 0.5. We are right on that. Okay. Now, so we are going to start off with 1000, right? So what will happen is we can go stage by stage. We can go step by step. But anyone can tell me how do I calculate immediately which binary level it will be quantized to? Anyone? Quite simple already, right? This one. So long as you have the resolution, everything is easy. Okay, anyone? Think about that. It will be 6.6. Huh? 2. What would it be? Anyone? 6.5 maximum, huh? Oh, you're saying that you will be rounded to 6.5, right? Yes, that's 6.5. Okay, 6.5. 6.5 is correct. So you take 6.6 divided by 0.5. Now, what number do you get? What is the decimal? Do you get 13 point something? Okay, what's your answer? Okay, guys, okay now. Yeah, 13.2. But you don't, there isn't a 13.2 level, right? So what happened is it will be truncated to 13, right? So 13 level, right, in binary is going to be 1101 in binary. Can? Right now, so finally in your SAR, right, the final output will be 1101, which will be inside your SAR. Right now, so now they're asking for the sequence of it, right? So what will it be? What will be the starting sequence? It will always be 1000, followed by 1100, followed by 1110, followed by 11. You'll be reset. Yes, then followed by, wait, one. Yes, so it'll be followed by 1101. Can? Okay, understand the sequence, because we set to 100 first. Always the MSB, the first step is always set MSB to 1, the rest to 0. Compare, the input is higher, right? Keep. Right now here, input higher. The second bit keep. Now input lower. Okay, reset. So this is the reset state. Okay, then 1101, input is higher. Keep. End already. Okay, so 1101. So that's the state. Okay, I think we are a bit tight on time. So now for the last question, I will straight away give you the answer. Can? Right, we are running a bit out of time. The last one is quite doable, right? It's quite easy. Can? Okay, let's go to the next question already. Now, SADAC has a digital output of this, and the maximum output voltage is 20 volt. Now, we count the number of bits first, so it's going to be 8 bits in total, right? So what is the resolution? Very simple. It is just the maximum voltage, which is 20 volts, divided by 2 to the power 8. Okay, so you get 0.078125 volts. Now, what is the input voltage range? What's the voltage range of the input? Now, so what are they asking is, because the input is digitized as this, so they're asking for the range of the input. Okay, so now what we are going to do is very simple. We have to find out this number in binary correspond to what number in decimal. So it's 167 in decimal. So at the level 167, right? So how do I get the corresponding voltage? It will be 167 times this, and you should get 13.04 6875. Okay, now take note, whatever that we are doing is we are truncating down. We are rounding down. So it means that the actual analog input, right, must be between what? 13.04 6875. So that should give you 13.125 volts. Okay, I hope you guys are getting because because no matter how much it miss, it just miss by a little bit, it will be truncated, it will be rounded down. Okay. So guys, we are going to maybe take a very short 5-minute break. I think we should still be able to finish. Okay, so let's go for a short break, right? Then after that, we're going to complete the rest of the materials, right? And then that will be the end of the lecture already. Yeah. So okay, I'll see you guys in 5 minutes time, right? At about 10:23. Okay, try to come back in 5 minutes time. Okay, see you guys in a short while.
Recording stopped. Recording in progress.
Okay guys, welcome back. We're going to continue on the second part of today's lecture. I think we have, let me see. Okay, another few more pages to go, right? I think we should be able to complete this. Okay, now, so we have been doing analog to digital conversion. Now we're going to do the reverse. So now that the computer has received the digital signal from after the analog to digital conversion, right now, after you have done your signal processing or whatever, then finally you want to output it to somewhere, or maybe you want to output it to a speaker or to transfer the data or whatever, right? So you need to recover back the analog form, right? So the function of the DAC is to convert the digital data back to the analog form. Okay. Now, so if you listen to the digital form, right, it's going to sound very maybe in our senses, maybe it sounds more metallic. It sounds more you feel like the sound doesn't sound correct. Okay, so what you need to do is you need to decode it first. Then after that, you need to go through a smoothing process. Okay, a signal smoothing process, right? So we are not going to talk about the smoothing process. We're only going to talk about the digital to analog at that level. Okay, we are just converting it back to a analog signal. The smoothing part is beyond the scope, okay, for this module, right? So the decoding part, right, is the process whereby the digital data, right, in binary bits gets converted into the analog data. Like example, just an example here. So maybe, right, gets converted to 5.1 volts, something like this, or 5.12 volts. Okay, something like that. Okay, so what is the analog voltage output? Is always generally in this form. So what we have here, right, is now I should put it in a way that is more you can understand better, and that should be whatever VREF that you have, right, multiplied by the actual bit multiplied by half, the binary bit multiplied by 1/4 plus whatever bit that I have, and multiply by 1/2 to the power of n, right? Depending on how many bits you have. Okay. Now the naming of the bit is a bit different. So this refers to the MSB, and this one refers to your LSB. And in different literature, they use different convention. Some put BN in front and B0 at the end, and some put B1 as MSB. And so I think what we need to understand is that the MSB always have the biggest fraction, which is half, then followed by 1/4, and so on and so forth, right? So take note, irrespective, whatever literature that you are looking at, right? The one that has the biggest fraction is always the MSB. Can? Right. So okay. Now, so the thing about DAC, right, is that the process is a lot simpler, right, compared to the ADC part. Because what we are doing here is, I'm not talking about the smoothing part, we are talking about just the conversion part, right? So it can be done quite easily, right, using a resistive network consisting of resistors and just op amps, right? Then you can create a circuit to do it. That's why we use a DAC in the previous ADC conversion circuit. Okay, now so let's straight away jump to one example that we have here. Okay, so now I have a 4-bit ADC. This is a 4-bit DAC. Now the input to this is a digital input of 1001. So now I want to find out what is the output voltage, which is an analog voltage. I want to find out how much this is. given that the reference voltage is 5 volts, right? So simple. So the V out would be equals to the Vref, then remember half times the MSB, right? 1/4 times the next one, plus 1/8 times the next one. Okay, and this is 4/16 times the LSB, right? So this is how it works. Okay, now, so, okay, from here, okay, we can do the calculation quite easily. It will be, now the reference voltage is 5 volts, so half times, now in this case it's 1, then the rest is 0. Okay, let's just write it down. 1/4 times 0, 1/8 times 0, plus 1/16 times 1. Okay, and you should get 2.8125 volts. That's all. Okay, calculation very simple also. Now, once we come to this, then we are going to look at circuits. Altogether, I think there are only 2 circuits, one more complicated and one less complicated, right? So there are only 2 circuits that we need to look at, right? And one of them is what we call a binary weighted, right? So this is a binary weighted input digital analog converter. Now, can anyone recall from the op-amp part, what does this circuit look like? Which amplifier is this? Which op-amp amplifier is this? Very good. This is a summing amplifier. Well done. Okay. I was thinking that maybe half of you have forgotten it. So this is a summing amplifier, and this is perfect. This is perfect for a DAC conversion. Okay. Now, so what do we have here, right? This is a resistor network. Now, what is nice about this is that, can you see? I can make use of the ratio. I can make use of the ratio of the resistor, right, to get my half, 1/4, 1/8. Now, if you guys do remember what your summing amplifier do, right? This is how your summing amplifier look like. Let's say this is 1 kilo ohm. This is 3 kilo ohm. This is 7 kilo ohm. This is 10 kilo ohm. So this is V1, V2, V3. So what does this summing amplifier do? The V out is minus 1/3 V1 minus 1/7 V2 minus 1/10 V3. If you guys remember this, okay? So it's a inverter and a summer at the same time. Okay, so this is what we call a summing amplifier. So what we have here, right, is the DAC version of a summing amplifier, and you can see that the resistors are just going to be starting from R, double of it, 4 times of it, and 8 times of it. That's all, right? Now, there comes a problem. The problem is that if you have, think about it, if I have, this is 4 bits. If I have 8 bits, right? The resistor value difference is huge, okay? And practically, it's very difficult to get the exact resistor for this kind of application. So although this is a very simple implementation, this is not often being used. But anyway, let's just look at, because it's simple, it's easy to talk about the theory behind it. Okay, then after that, from here, then we move on to something that is a little bit more meaningful or easier to implement in practical situation. So basically what we have, right, is that you can see the R, 2R, 4R, and 8R, right? So these values represent the binary weights, okay, of the input bits. Okay. Now they say that each of the input resistors will either have current or no current. So example, if this is 1001, right? So there will be current from here and here. Those with input of 0, there will be no current. Okay, right? So if the input voltage is 0, the current is also 0, right? If the input voltage is high, then the amount of current depends on the resistor value. Okay, and that's how you get your voltage value. Now, we will go through the theory simply, then after that we can do the example questions, because this is quite quite easy to understand. So the resistor values is going to be 2R, 4R, 8R, Now, if you have more bits, you'll be 16R, 32R, 64R, and 128R. So that is what I mean by it is not too practical if you go beyond 8 bits. Beyond 8 bits, right, you already have to go to 256, 512, and 1024 times of this resistor value. Okay, now, so what do we have here, right? 2R will correspond to a binary of 2 to the power of 2, right? Don't forget, because your 2, the resistor that is over here is in the denominator for the summing amplifier, right? So this one and this correspond to 2 to the power 1, and this correspond to 2 to the power 0. Okay, so on and so forth. Right, let's see. Yeah, I think there is an example that I want to look at. Now, so what are the disadvantages, right? You need a lot of different resistor values. And it is very difficult to get resistor values that are like double, quadruple, or 8 times of the original one. It's not easy. Practical resistors are not the values are not increased in that way. Okay. So we're going to do one example here. So I have a DAC here. I have a DAC here, and what is happening here is that the inputs is 1001 in that sequence. This is MSB. This is your LSB. Okay. So now question to all of you. Which one of these correspond to the MSB? Right? Which one correspond to the MSB? D0, D1, D2, D3. Think. MSB. D3. Okay, there's a D0 and D3. Right? Why D0 and why D3? Now, don't forget, your V out here is going to be minus RF over R1 times your voltage input, right? And so on and so forth. The smaller the resistor value here, that means you will have a bigger weight or a greater weight. Okay, so please take note of that, right? So which one should give you a bigger weight? It will be D3. Okay, D3 will give you a bigger weight, right? So I'm going to show you how to do a calculation here. Now, so what we have, right? The logic level here is 1001. Okay, now but when we talk about logic level, right, we also have to ask the logic level ones correspond to how many volts electrically. So the voltage here, right? Let's say this is 5 volts, 0, 0, and 5. Okay, when we do the calculation, it will be based on the voltage that we have here. Okay, so I did not include that in the question, so we are going to mention here. Vref is equals to 5 volt. Okay, now so what do I have here, right? The V out will be negative 10 over 25 times D3, which is 5. Okay, right. So from here, I should be getting negative 2.25 volts. Okay, so guys, just to inform everyone again, now this Friday, the lesson will be, we will not do the quiz during the class. The quiz will be arranged separately. So we are going to spend the 1.5 hours, right? And whatever that we have not done for topic 3. Okay, so it will be topic 3, then topic 5. Okay, then the quiz number 3, I will be letting you guys know when to do the quiz 3. I will give you a time to do that. Right, you'll be doing it online with a lockdown browser plus the responders monitor. Okay, so moving on. So the last, we still have one more, right? Okay, so right, let's take a look. Okay, now so please take a note. In order not to, now this circuit here, right, is a little bit smarter here. What it does is that because the output here is negative, right? The output here is negative. So you will still need to go through an inverting amp, right, to make it become a positive voltage, right? So what happens is, then someone thought of, okay, why don't I change the reference voltage to negative so that I do not need to go through one more stage, right? So this is what happens here, right? So what happens here is, you guys can see from the diagram, right? This is 0 volts here. So it will be 0 volts here. Now, can anyone tell me what's the voltage on this side? What's the voltage here? Negative 10. Yeah, someone mentioned negative 10 is correct because this is a battery. The positive connected to ground means the negative part will be 10 volts lower. Very well done on that, right? So the voltage here is going to be negative 10. Now, so if you look closely, right, this 3 connection is connected to minus 10. Now, can anyone tell me what is the digital input to this DAC by looking at the switches connection? So the switch is, oh, very good, well done. Okay, it's 1110, 1110. Well done, because the switch here is connected to a negative 10, negative 10. So let's draw this out. Okay, very well done on that. Okay, and the last one is connected to ground. So you have 1110 right now. So in that case, then I think it should be very easy already. Your V out. It will be, okay, the reference voltage will be minus 10. Then it will be half, minus half times 1 minus 1/4 times 2 minus 1/8 times, times 1, sorry. So this is your D3, D2, this is your D1. Then your D0 is 0. So you can omit it, or if you want to put it, you can just multiply by 0. Right. So your answer here, I believe you should get 8.75 volts. Okay. Now, so moving on. Okay, we have the last circuit already, right? The last circuit is another digital to analog converter, right? It's called the R/2R ladder digital DAC. Now, this one is very special because you only need 2 resistors, right? You only need 2 resistor values and you can replicate the whole circuit, right? So what we have here, right? I think there is a mistake in the diagram. This one should be R, okay? Now, if it's 2R, you can't get the ratio half. So I think there was some mistake in the publication that did this, right? So this is the R2R ladder. And okay, you only need 2 resistor values here. Now, how to analyze this circuit is very complicated, right? And you guys have not learned circuit laws like Thevenin law and whatever. So what I'm going to tell you is that the way of calculation is the same as the previous one, right? So there is no difference in the way that it's being calculated. Okay, so you just need to know that, oh, this is D3, D2, D1, D0. So this is the MSB and this is the LSB, right? Now, after your circuit law, then you come back to this, then you will understand why the ratios are like that. Okay, so what's happening here, right, is that the 3 resistors down here is all the same, right? Then this is twice the resistance value, right? And then the feedback resistor is R. Okay, now so what I'm going to do is to just let you see how it's being connected, right? Then after that, let's do a calculation, right? So example, what we have here, right? In this case, you can see that again, this is your ground. Okay, quite a smart design. This is your 0 volts, right? On the other side, this is going to be negative 10, right? So here, can anyone tell me for this particular example, right? What is the digital input? Anyone? Yeah, same thing. So it's still going to be 1110, right? Because your negative 10 volts is connected to this tree, whereas the other one is connected to ground. Okay, now, so what I have here, okay, every time, for every of this is going to be, for every of the branch here is going to be half, right? So now, let's just do a very, very simple example, right? Then we have to end the lesson already. We are running a little bit late. Okay, now, so Now the digital input here is 1110, right? Reference voltage is 10 volts, right? So the question is asking to find the output voltage. Now, sometimes the question might not give you in the actual input. They will ask you to interpret from the diagram. But even so, this is easy, right? So we just need to see which one is connected to ground and which one is connected to, right, the reference voltage. So this is again 1110. Okay. Right. It seems that a lot of I got the diagram from different textbooks. They seem to like to use 1110, right? But anyway, so what we are having here, right? So your V out is just going to be equals to V reference, right? Then the ratios for each of these. So you are going to have minus half times the MSB bit minus 1/4 times the next bit, which is also 1 minus 1/8 times the next bit is 1 minus 1/16 times 0. Okay, so if you work this out, you are, I think it's the same question as just now. It's just that, so this is going to be minus 8.75 volts. Right. Okay. Right. Now, so if you look at this, this is going to be giving you a factor of minus half. This is going to give you a factor of minus 1/4, minus 1/8, and minus 1/16 accordingly. Okay, so guys, I will see you guys on Friday, which is the last lesson already. So if you have any questions, just ask pertaining to any of the topics, right? So this Friday, please prepare on your topic 3 and topic 5, the tutorial. And again, I will be telling you guys when your online quiz is going to be, right? So please check your Excite announcements. Okay. Any questions before I end the final paper? Not easy, but there will be enough parts for you to, there will be enough parts to get, okay, there will be easy marks. Okay, there will be easy marks. There will be also difficult questions. But will the paper kill you? I don't think so. Okay. There are some parts which is meant to be a little bit more higher order thinking, but generally there will be more than enough parts for you to get all the what we call the low-hanging fruits. There's a lot of low-hanging fruits. Okay, so to maybe get in the range of 60 to 80 for the paper, maybe 60 to 70, I was 70 something will be easy. Then there'll be some marks which is a little bit more difficult to get. Okay, but passing the paper, no problem.
Sir,
Yeah.
is there any additional tips or any information that you can share with us regarding the
Additional tips.
yeah, besides what you just mentioned?
Additional tips. Tough, like, because you guys did too well for midterms, right? I've not received the final marks from the lab yet, so yeah, I cannot promise anything at this point of time, but we will see. We will see. Okay, we will see during the tutorial class on Friday.
Okay.
Yeah.
Thank you, sir.
It's going to be 4 questions. I think I mentioned before the breakdown is 4 questions. Then chapter 1, 2, 1, chapter 1 and 2, 1 question. Chapter 3, 1 question. Chapter 4, 1 question. Chapter 5, 1 question, and all equal. 3, 4, 5 is all 25%. Then 1 and 2 add together 25%. Okay.
Prof, you got any declaration you want to say? Like, for instance, our quiz, you say not a lot of people will follow, will be able to complete it. The finals, will there be the same situation?
Finals, I think you have more than enough time because your finals is 2 hours then. Don't forget. Probably a lot of you will walk up at 1 hour 30 minutes. I feel. Because yeah, this module, yeah, I don't think there will be a lot of you that will, yeah, it's a 4 question 2 hours. One question half an hour, more than enough time. Okay, 4 question, it's not 5, it's 4. Yes, have obviously there will be different parts, and some of the parts are not linked. Okay, so within 1 question you can have like chapter 1, maybe 1 question, 1 part, then question 2 will be another part or something like that. So there will be multiple parts. Okay, any other burning questions to ask? No. Next try, no more. The other group, yes, but not this one, not this. Because I think the next group, tragedy. Tragedy means that with me taking you guys, it will be a tragedy. What is the point? It's 25% per question. No, I have to tell you, different lecturers will have different teaching style, right? Whichever that you like, it doesn't get to you for you to choose. So you have to understand that when it comes to the next um the next trimester, right? You might need to adjust totally because okay. So the thing is, you guys need to adapt. You come to uni, is all different lecturers, and you just have to adapt. Okay, and the faster you adapt to it, then you have to you learn faster, right? And if the faculty cannot help you much, I would suggest please go and do a proper literature research and not just depend on ChatGPT. Okay, sometimes whatever ChatGPT give you might be wrong. In fact, I look at a lot of information that you get from ChatGPT, right? I seriously, it is better to look up a respected channel or a avenue, right, which gives you the correct information, because I am seeing too much of error that comes from either ChatGPT, or if you Google Google and you do not go for those respected ones or the authentic ones. Okay, so this is the trouble that you guys are facing. My generation don't have, because when my generation, we go to a library, and if you look up the books, it will definitely be correct, or 90% you'll be correct. Okay, but nowadays, you Google, right? Maybe 70% is correct, 30% is wrong. Okay, so it's a struggle for you guys. Okay, I understand you when you have a lot of conflicting information that comes in, right? It's actually impeding your learning process. Okay, so guys, right, thank you so much for that this 12 weeks of fun and laughter. Okay, so I will see you guys on Friday. Then after that, I will see you guys for exam, and I hope that I won't see anyone for a remote or a receipt paper. Okay, right? Okay, so I have to end already. So all the best for all the exams that you'll be taking. Right. So thank you. See you
Thank
guys.
you, bro.
Right. See you.